That's absolutely amazing. You have something that weighs as much as the sun, so 2 times 10 to the 30 kilograms, and the radius that you just calculated, assuming it's a black body, and that's what stars are to first order, is only 5,800 kilometers. That's less than the radius of the Earth. So you got something the size of the sun, or the mass of the sun, crammed down in something the size of the Earth.
Yes, you can work out the density, just divide the mass by the volume of a sphere, 4/3 pi r cubed, and you come out by 2 by 10 to the 9 kilograms per cubic meter. 2 billion kilograms per cubic meter.
Right, so that's a huge amount relative to water, which is, for example, 1,000.
Yeah, you can find out if you have a teaspoonful of the stuff, it would weigh you 10 tons.
Well, on Earth, at least. So that's under the Earth's gravity. So the gravity on the surface of this star must be enormous.
Well, you can calculate that as well. Let's say, for example, what's the force on a typical, let's say, roughly 100 kilogram person? You can use the usual Newton's law of gravity and plug in the mass. The mass is the same as the mass of the sun, but the radius is much smaller, so the gravity, and of course it depends on 1 over radius squared. So that means the gravity is going to be way higher than the Earth, first of all, because the mass is much higher than the Earth, and a tiny radius. And it turns out the force is about 400 million newtons on a typical person.
Ooh, so that is a lot more than, for example, that's just like I would weigh, well, I don't quite weigh 100 kilos yet, fortunately, but that means I would weigh about 40,000 tons rather than what I would weigh here on Earth. And
yeah, so about as much as an oil tanker or something like that.
I don't think my bones and body would do very well if I weighed that amount.
Yep, so this gives us a puzzle, because we've got something that's very hot and absolutely incredible pressure, presumably, from all this gravity forcing down. Surely that means it's going to undergo nuclear fusion. I mean, we know that nuclear fusion, when you combine nuclei like hydrogen together, we know most universes are made of hydrogen, so our first guess must be that these are made of hydrogen like every other star that we know about. And if you push hydrogen together with enough pressure and temperature, the hydrogen nuclei will fuse and generate energy. So presumably this is a very good place to have nuclear fusion.
So we should be able to calculate pretty straightforwardly the pressure and the temperature type conditions and compare it to, for example, our sun, and see if we expect fusion to be going on there.
Okay, so let's do that.